Hi, I'm Dr. Papia Bhattacharjee. In this problem, we have to compute the volume of a solid region, and it's given that the region is bounded by the graphs of these functions. So we have z equals x, y equals x, then z equals 0, y equals 0, x equals 0, and you know these three basically tells us that it's in the first octant, and then x equals 4. Okay. Now, let's try to understand this three-dimension figure a little bit. So, z equals x, you know what line that is, that's in the xz plane, and right here this is z equals x. And then we have y equals x is also a line in the xy plane. So, if you consider the xy plane, this line is y equals x. And if you come down here, the x equals 4, that's a plane passing through x equals 4 and parallel to the yz plane. So, this is our x equals 4 plane, and here is 4. Okay, so you kind of visualize what the solid will look like. That's bounded by this plane, the line, this line, and all the first octant planes in the xz, yz, and xy coordinates. So, here is our solid. Okay. Now, we have to compute the volume of that solid. So, remember how to compute volume using double integral. So, we will have double integral over region R, and what is R? That is the xy trace of the solid, wherever the solid is intersecting the xy plane. And then we have the function and then the area of the rectangle inside the region, that's dA. Okay. So, what function do we have? So, that's the z, right? What is the z equals? And notice we have z equals x. So, that's our function. So, our function is x. So, let's write that down. Function is x. And then we have to figure out the region and then figure out if dA is dx dy or dy dx. Okay. Let's come back to our solid here, and you see the x-axis and y-axis. So, this is our xy plane, and here is our solid. So, where is it intersecting? Well, it's intersecting right here. Do you see that in the xy plane, right? So, what are the different curves that are bounding this region? So, one is the x-axis. So, let's try to graph it in the two-dimension plane. We have x-axis, and then what is this line? Well, this line, see, it's the plane through x equals 4. So, this line is also the line x equals 4. Okay. So, let's draw . Say x equals 4 is somewhere here. Okay. And then we have this line, that's y equals x, right? So, let's roughly try to graph y equals x. And so, the region that we drew here is same as this region. Okay, this is our y equals x, and x equals 4 and the x-axis. So, this is region R, and now we have to figure out what are the bounds, the x bounds and the y bounds are going to be. For that, we need to draw a rectangle inside the region. And notice that the width is delta x. That means x will be the outer variable. Now, let's see the bounds here. X lies between which 2 points? Well, it starts at 0, ends at 4. So, x is between 0 and 4. And what about y? You have to look at the length of the rectangle now, and it starts at x-axis, which is y equals 0, and ends at the line y equals x. So, these are our bounds for the region R. So come back here and let's write down x is the outer bound. So we have 0 to 4 on the outer integral. Y is the inner bound. So 0 to x in the inside one. And then here we will have dy dx because x is the outer variable. Now that we have our setup for the double integral, we just have to compute them. So ignore the outer integral and just evaluate the inner one. Remember, this is in terms of y, which means x is a constant. So x, write it down by itself, and antiderivative dy is just y. Evaluate from 0 to x dx. So this is equal to, so keep x as it is. For y, plug in x and then plug in 0. When you plug in x, you just get x, but when you plug in 0, you get 0, right? So this is just x times x, which is x squared dx, and the antiderivative is x cubed over 3 from 0 to 4. So that is 4 cubed over 3 minus 0, because there is an x already. So this is 64 over 3. And since this is a volume, this is cubic units. So the volume of this solid that's bounded by the graphs of all these functions is 64 over 3 cubic units. Thank you.